Hey everyone, this video will actually mark the start of our calculus journey, and we'll start off with differentiation. Before we talk about the actual definition for differentiation, I would like to consider a graph, alright? Let's say you have this graph, okay, let's make it less curvy. This graph here, obviously, let's say we have the y and x axis, so let's say this is x, and this is y. Let's say, in your science practicals, we'll find the gradient at A. What some of you might do, or actually this is what you're taught to do, is that we will try to estimate this gradient. We have a ruler with us, and then we will, make it such that it just nice touches the point and not much other points as well. And let's say, seems like good enough, and then you draw a straight line through. Then what we are taught to do is that, well, okay, we'll pick a point, let's say over here, usually the x or y intercepts. Then you pick a further point, we then take the gradient, and then we will say that, okay, gradient at this x equals to a value is so on and so forth. There are two inaccuracies I think pretty much is quite intuitively found. Firstly is that you're taking 2 points that are not on the graph, right? That's not on the actual curve, so not on the original curve. And secondly, you are estimating with your ruler, and is therefore prone to a lot of errors, and it's not exactly very scientific. Let's deal with this problem first, okay? The 2 points on the original curve. Okay, so first we have the same graph. So let me get back to my black pen. I'll draw it longer this time around so I can show you in terms of explanation. Okay, now I have a better looking curve. Let's say the same point again at x equals to a. Let's say somewhere around here. And this is x equals to a. Obviously, if you want to use the point x equals to a, you will want to include the point x equals to a, so we'll take this point here first. So whatever this point is, we'll take it here first. Then what we do is you find some point on the graph, let's say over here, further down. Okay, so say from here. And because we know that this is more than a, we label this point as a plus h, where h is a real constant and it's positive. Then we'll take the gradient. So let's say I draw my first gradient as red. Okay, so say this point here, and then marking this point here. I will then draw my gradient. Okay. Clearly, this gradient is not exactly the tangent to the graph. So what we'll do, we'll move it closer. Let's say we get a closer point here. Right, now I need to zoom in a bit, so pardon the quality. Okay, so at this point here, we have, again, a plus some h0. Of course, h0 is less than h, and therefore a plus h0 is closer to a. Now we take out our ruler again. Let's draw the gradient. Alright, so I have one thing here. I have one. Oh no. Okay, I'll zoom in more. Okay. One of it here, and I zoom in even more. Okay. Wow, this is fantastic. Don't worry, I'll zoom out later. Okay, get it here. Let's say blue. Draw a gradient. What do you notice? You notice that as it gets closer, the gradient between the 2 points almost starts to form the actual tangent to the graph at the particular point A. And if we are to continue that trend, let's say it gets even closer and closer, I think you would soon see that this gradient between these 2 points would then yield a straight line that would virtually be the gradient of the tangent. So let's say we have a very close point here, and we draw a line that marks the gradient is almost a tangent. And therefore, this is the whole idea of differentiation. Is where this point, this adjacent point a plus h. So let's say I have a value fa plus h minus fa because this is the gradient, right? And then we have h. As this a plus h gets closer to fa, so as h approaches 0, as a plus h approaches a, h will approach 0, this function here would then yield us pretty much the gradient of the graph at the point x equals to a. And this is the whole idea of differentiation, is where we want to find the instantaneous rate of change. So instantaneous rate of change, ROC, of a variable. So could be any variable, could be x, could be y. For the sake of the example, I'll use it as y, to the rate of change of another variable, where this variable, the latter variable, is actually fixed. And this basically gives us differentiation. And differentiation will yield us the function that represents the different gradients, or sometimes the same gradient, at different points. And therefore, to represent it mathematically, as h approaches 0, that means as the point gets closer and closer to the point that we are interested in, our gradient would be this. You can try with any graph you want to. Let's say if you want the EX graph or whatever x squared graph, you notice that you can take the point, let's say find a gradient at x equals to 2. You find the gradient at x equals to, let's say, 2.002, and then so what, you can add 1 decimal places if you want, and you notice that the gradient is incredibly close to 4. Okay, I know this because I know the actual derivative of x squared. Alright, so let's say it's just the x, y equals to x squared graph. And you notice the derivative gets very close to 4 and is therefore a good estimate of the gradient. And this is the whole idea of differentiation. Alright, and coincidentally, this is what we call by the first principle. As such, alright, how do you represent this function? A few notations. It really depends on what your variables are. If let's say we have y equals to fx, so let's say if y equals to fx, let me just box up this definition first so that you won't be confused. Okay, y equals to fx, therefore we have dy dx, dy dx, just right, we're reading the letters. Basically, this means that the change in y over the change in x, basically the gradient, right? As h approaches 0, whatever y value you have at x plus h minus whatever y value at x over the change in x, which is just h. Alternatively, if y equals to fx, you can write f prime x or f bracket 1x. And this is what we call by the first derivative. So the derivative means the first difference. So after you differentiate the function once, you get back the first derivative. And this is actually the gradient. It's actually the gradient. Okay. Is there more derivatives? There are. If you differentiate once more with respect to x, you get d2y dx squared f double prime x or f bracket 2x. And this is your second derivative. Of course, this stretches all the way to however you want. So you can have nth derivative, and obviously we only narrow it down to two types of notation, because obviously if it's like very large, you're not gonna write like a lot of strokes, because obviously if like, you know, if like prime, it's just, you know, too time consuming, so we just don't want to write this out. So we simplify it to just f bracket n x. And this is actually your notations in your differentiation. Is it just limited to y and x? Well, not really. Let's say I have a equals to gb. If I differentiate with respect to b, I'll have dA, dB, I'll then have g prime b works the same as well. All right. And yeah, this is pretty much the introduction to your differentiation. We're looking at the instantaneous, because at the instant where x equals to this, or in this case, where b equals to, let's say, 3 or whatever, instantaneous rate of change of one variable to another. And then your first principles of dy dx, this is just a general form. As the h approaches 0, fx plus h minus fx over h, because as the points get very close, the gradient of the points between the 2 points, the line connecting the 2 points, would eventually become the tangent of the curve at the point x equals to whatever you want. And this is differentiation.